Alright, now comes the time of the operating system lecture number 6. And in this recap session of lecture number 6, we're going to talk about scheduling. And up until now, we've seen that processes, they're concurrent. They try to fight over the different resources in a computer. And I've repeated it so many times, the most important resource of them all in a computer is definitely the CPU, because it's with the CPU that you'll be able to progress when it comes to the execution, right? So you can get to execute your instructions. We've seen for other resources, we've used some different mechanisms, and we've already talked about those in earlier lectures. So we need to make sure that if a resource is already occupied by some process or thread, so whatever is true for threads is also true for processes, and the other way around, because threads at the end of the day are nothing but mini processes in a way or another, so sub processes in a way or another. So we order the access to the different resources using different mechanisms and tools that are offered usually with the operating system, and the most exclusive one of them all would definitely be the mutex, for instance. Or we can even use a monitor in order to order the access to the different resources. Now when it comes to the processor itself, to the CPU, well, this is a whole new paradigm. We're gonna try maybe and enforce some policies in order to make sure that the overall performance of the system is not being penalized, or not being degraded. And from now on, this is what we're gonna call scheduling. Fair enough, and this is what we're seeing in today's recap. So multi-programming system means that we have a bunch of things fighting over resources. So we have concurrent processes, and again, when it comes to concurrent processes, we need to be extremely careful about race conditions and stuff like that. So the first one to get to a variable or to a resource might alter that particular variable or resource, and the outcome could be different from the one that is intended by the designers. So we should be extremely careful when it comes to concurrent processes. And the processor, or processors with an S, plural form of it, because a machine might have more than one CPU. Again, I've said it over and over, and I'm going to repeat it one more time. If nothing is said about the number of processors in a machine, you're gonna assume that systematically we're using a single core machine. So scheduling is all about assigning processes, so order them, assigning them to the CPU in an orderly manner to be executed over time, and that should respect some objectives such as response time, throughput, that we've already seen in the CA course, and we're going to have a quick reminder of it, and overall processor efficiency. And of processor efficiency, you've covered that in one of your tutorials and practice assignments, when you try to overlap different jobs in order to make the best efficiency of the use of the CPU. Alright, so here we're familiar with the 5-state diagram of processes. Where's my pointer? And you've seen in one of your tutorials as well that we can, this is not the only one, and we can have a really minimum one, which is running, not running, for instance. And we can even have more states and some representations as well. So this is just an example model that we're using, and we're gonna see how scheduling, where scheduling, in what state does scheduling take place. So go ahead, pause the video for a second and try to think about where do we schedule from where if we're trying to get to the running state here. Remember, this is what's concerned with the CPU. So where do I go ahead and schedule? So yeah, once you thought about it for a couple of seconds, I'm gonna introduce two types of scheduling. So if the first time would be long-term scheduling, and the idea here is how to create a process and admit it to the system so it could be ready for execution, and this is what we're gonna call long-term scheduling. So where would that be here on this map? So it would definitely be here. So we're admitting a new process. So a program, before becoming a process, is just sitting idly, like passively, in the secondary storage, not in main memory, and then something happens and it's ready so it can get the CPU to execute. But before getting ready, it needs to be created, and this is the objective of the long-term scheduling. So now if I tell you that there's a type that is called long-term scheduling, what would be the other type? Well, it would be short-term scheduling. So once we've admitted the process and it's in the ready list, which one from the ready list we're gonna go ahead and pick up and assign to the CPU? Right, so these are the two types that I want you to focus on. For your own knowledge, there's a different type as well, medium-term scheduling, but I mean, I don't really care about that in this course. And the one that we're gonna really tackle in details and cover in detail is definitely the short-term scheduling. That's why it's in red. Alright, so just a couple of words about long-term scheduling before hitting the short-term scheduler. So a program that is not a process yet, well, the long-term scheduler will decide which among them will be a process, will be admitted as a process. So we will assign a PCB to it, we will have some portion of the main memory for it, so it can get ready to be executing. Now, naturally, we'll have two questions. What would be those two questions? First off, well, when? So the time. When are we going to admit or create a new process? When to afford it, etc. And on what basis? So basically, if I have a bunch of programs that are going to become, that want to become processes, so a bunch of programs that are requesting to become processes and be able to execute, well, which one of them we should admit? And one random answer to that, by now you could say, well, the first one to ask to become process should be the first one to become one, or it could be in a random matter, or there could be some priority. So we can imagine a lot of scenarios here. So once admitted, so a program will become now a process, and it has a PCB, and it has all the data structures that are needed for it to execute. And this would be the job of the short-term scheduler. Now the question is, well, if we have a bunch of programs that want to become processes, so the more processes I admit, the more programs become processes, that would definitely affect the overall system. Let's take a second and think about it. And by the way, here we're seeing a bunch of resources, and specifically two processors and a bunch of processes. And what can you notice? For instance, which process is currently active or executing in CPU2? Well, most probably it could be P5 here. What about the first CPU here? Well, it's P1. And here we can see that there's some kind of symmetric attribution, right? So some load balancing between the two CPUs. Fair enough. What do we call, by the way, when a process kicks out another process to take its place inside the CPU and the other one is still having something to execute? What do we call that? Yep, we call it preemption. Alright, so the more processes I create, should we use a time slicing mechanism, selection mechanism or scheduling algorithm? Fair enough. From now on, we're going to call it the scheduling algorithm. So the more processes I have in the ready list, and if I'm using a time slicing scheduling algorithm, this means that I will have less time per process inside the CPU, because I need to distribute the all in all time all over the processes present in the ready list. The more processes I have in the ready list, the less time for each process is attributed for the use of the CPU. And this is what we call the degree of multiprogramming. Alright, so the more processes I have, for sure I will have more things going in parallel. However, the time slice assigned to each process will be lower, shorter. And this means that it will take more time for a process to execute. So it's always a trade-off here. And the answer to the other question is, well, which one to select? Well, usually they go on a first in, first out. Another name for that would be FCFS, and this stands for first come, first served. Or I can use it to manage system performance. Let me think about it for a second. Imagine that one of the programs will extensively use a resource, and there are already in the system a bunch of processes that are using this resource. Let's imagine that the resource is the printer. So program A, which is still a program, not a process yet, is apparently it needs the printer, and in my ready list I have process 1 to 6, and all of them are already trying to use the printer. This includes all the organization and the mechanisms we need to use in order to order the access to the printer, etc., etc. So would it make sense to admit program A to become a process 7 for instance, and then add it to the list of the processes that are going to use the printer? Or just go ahead and use program, I don't know, C, right, that has nothing to do with any resources, just wants to execute a couple of things. So most probably, in order to manage performance and a little bit, if there's some kind of strain on some resource, well, it would be easier to take the program that doesn't need the resource. Alrighty, short-term scheduler now, and this is what we call also the dispatcher. And this is what we talked about earlier in a couple of lectures ago, and we didn't used to make a difference between the scheduler and the dispatcher, but now technically you know what's the difference between a scheduler, which has many types, and one particular type of the schedulers is the dispatcher, which is the short-term one. So here I'm gonna pick up which process to execute inside the CPU next, and it's really fine-grained decision. It means that it's really close to the CPU. It's from the ready list, and this is the most frequent scheduler that execute most frequently. Usually it's every time tick, every tick. Usually it really depends on the implementation, but I mean, grosso modo, we're gonna say that it's every time tick. So yeah, when is it the dispatcher invoked? Usually, as I said, every time tick. And from the very first video and the very first face-to-face lecture, we said that everything in the system from an operating point of view is organized in something that says that now it's ready, now it's not ready, now you can leave, wait for it, and someone will notify you about it. So the whole thing is called interrupts. So everything is interrupt based in a way or another. The easiest interrupts of them all is the clock interrupt. So every tick is actually a clock interrupt. Fair enough? And if we don't want to use the clock interrupt, the ticks, and to make the decisions, we could imagine different other scenarios, such as once I'm done using an IO, once I'm trying to use an IO, once I'm done using a resource, once someone is done using a resource, etc. So any kind of interrupt could be used to try to invoke the dispatcher to choose which process to execute next. Alright? So whenever an event happens, something is notifying the system that now you need to make a decision to choose the next process to execute. Right? So IO interrupts, system calls like programmed interrupts, also known as traps, clock interrupts, the easiest one of them all, or anything related to the semaphores, for instance, because it's a signaling mechanism after all. All right. So what is the main objective of short-term scheduling? Well, or the dispatcher? Well, I'll have a bunch of system behavior, so a checklist, things that I need to respect to try to optimize, right? And I'm gonna go ahead and try to order my ready processes in a way that I'm trying to maximize or minimize the things that I want to maximize or minimize. What is, out of your head like that? What would be the thing that I would like to minimize? I mean, the ultimate goal is to minimize what in order to improve performance? Well, to minimize execution time. Fair enough. What would I like to maximize, for instance? Maybe the number of processes being executed in a defined period of time, and this is what we call throughput, for instance, as seen in the CA course. All right, so yeah, so the scientists decided, and in the scientific literature out there, they decided to divide those criteria into user-oriented and system-oriented ones. And let's do that. Turnaround time. So in class I made people try to read it and explain it to me, so you can do that at home as well. And you can see that turnaround time is all the the whole execution time plus any time that you'll be waiting for resources or waiting in the ready list. So if I'm going back and forth between ready and running, well, I'm going to take into consideration all the time that I'll be spending inside of the ready state as well, and any time that I'll be spending in the block state as well, to know the overall turnaround time. And by definition, it's when a process is admitted to the ready list for the very first time. So this is when it was admitted by the long-term scheduler for the very first time in the ready list. So it was created and became ready until the very end of its execution. So the completion of the very last instruction in that process. And this is what we call the turnaround time. It's from A all the way down to Z, including any waiting anywhere in any state. There's another time that I'm interested in, the criteria. It's response time. So response time, well, it's the time from the very first time that the process became ready until the execution of the very first instruction in it. So it's starting to respond. So you can feel that there's some kind of interaction happening. It's responding. It's giving something. It's starting to give something. So you can feel that response time and turnaround time are related in a way. How would they be related? Think about it and answer yourself. Well, one of them is included in the other. Finally, deadlines. It's exactly like for your projects. You'll have some deadlines and you need to meet them, right? So this is one of the things that I need to maximize. For instance, when it comes to scheduling, well, I need to make sure that all my processes are meeting their deadlines. If not all of them, well, all of them but one, to maximize the number of processes that are actually meeting their deadlines. Fair enough? So 3 criteria here. And we're gonna move on. Predictability. Right. So remember when we talked about processes for the very first time, and we said that we're creating a process image each and every time we're trying to admit a process into the system. So whenever you double click on your favorite, program that you want to use at home, but you're not creating the actual program, you're creating an image of it because it's related to the day of time of you double clicking on it. And the very next day, if you do the same, while you're creating another image, it describes it englobes the same process. However, it's a different image of it. So the idea here, if you're you want to play a game on your computer and you're expecting that there's that much lag in the game, so it doesn't freeze that much, or it freezes maximum 1 second, let's say, or the loading of the game will take 3 seconds. So you want it to be always 3 seconds, and if you're able to control that, this means that the system is predictable. So even if you're playing music, watching YouTube, doing things, and you're starting your game, the loading time will always be 3 seconds. This is being predictable. I know exactly how much time the job, the program, the process will run, regardless of the loads, of the current load of the system. Right, more criteria, throughput. So if we define a unit of time, how many jobs or processes are completed? This is from the CA point of view. Processor utilization, well, you need to try and have your processor as busy as possible. So theoretically, and as seen in your earlier practice assignment, we need to occupy our CPU to 100% theoretically. But I mean, in practice, if we're being pragmatic, like the good engineers that we are or about to be, well, it's usually around 99% or 98, 97, it really depends on the system. Anything around 95 till 99%. How come? Why is there some kind of difference between theory and practice? Why would we use, leave a little bit of percentage there? Well, the answer is, well, sometimes if you don't have a fully predictable system, which is extremely hard to implement, by the way, well, it's always nice to have some kind of security margin, some margin to deal with a sudden burst or something that you didn't think of, something that is unpredictable. Fairness. Yep. So if I'm not using priorities and I want to make sure that my processes are treated in an equal manner, in a fair manner, and we need to make sure that no process is ever suffering from starvation, especially CPU starvation. This is if we're not using priorities. And one of the examples that we talked about earlier, without getting in details, it's the time slicing thingy. Now, if I want to use priorities, again with the example of from cars, inside a car you have one CPU, imagine, and you have a process that deals with the radio and another process that deals with the brake. Here you need to make sure that the process that is dealing with the brakes has the upper hand, has precedence. It has more priority than the one dealing with the radio for obvious reasons. So the dispatcher should definitely favor higher priority processes here. Right? Another criteria could be, again, if a bunch of processes are ready and most of them they want to use a resource that is already being used, wouldn't make any sense to just pick one of the processes to get them into the running state for them to be blocked the very next tick because the resource is still not available. So maybe the processes that are not looking to use resources or underutilize some stress resources should be favored. Right, now we talked about the criteria, and I've said earlier that we have two different types, so user-oriented and system-oriented. We played a game in class trying to assign each of the each criterion in one of those boxes here. So we have user-oriented and system-oriented, and then we have something related to performance and other. And systematically, by now you should know, especially those who are taking the CA as well. And every time I mention performance, two things should come to mind. Well, mainly one thing should come to mind. Performance is always related to time. So anything that has time in it, it should be related to performance. And the other thing could be we can fix time and go and witness something else, and we're gonna try and do it. So take 3 minutes or so and try to assign the things here, and then check if it matches. So turnaround time, it has time in it. It's definitely performance related, but the question is it user oriented or system oriented? Well, turnaround time from whose point of view? Well, if I'm I wanna, execute my program, a human being, want to execute my program, well, it would be nice to know when it's going to finish. So turnaround time would be related to the user and its performance related. Right? So I'm interested in when my program has finished executing. Well, if we follow the same approach, response time has time, so performance related. Response time, it's the first feedback that my program is giving me as a human being, so basically it will go under user. Deadlines, we're gonna go get back to deadlines. We're going to see this here. So predictability, well, it's definitely user. Remember, I want to play a game and I want the loading to be the same yesterday and tomorrow and after tomorrow and today. So basically it's not per se performance, however it's, you know, it would be nice to know. So predictability would be user oriented and other. Deadlines, it's here for sure. What about throughput now? So throughput, we're fixing a unit of time and we're checking how many jobs are done. And we talked about it in the CA. So CA, it's closer to machine. So where should it be? User or system? Definitely system, because it's closer to machine. And throughput is fixing the time and witnessing the jobs that are being executed, so it would definitely be performance related. Processor utilization, same thingy. Fairness, now it's the other, still in system, right? Because it's not the user that is witnessing firsthand what's going on here. And you can feel that this one will come here and balance resource will come here as well. Alright, so scheduling algorithms now, and this is what we use on the ready processes to know which one to select and when to select it. Alright, so imagine that we have 3 processes here. The question that the scheduler or dispatcher is going to ask itself, well, which one will go next? You know, which one will be picked up first and which one will go next? And when should I go ahead and pick it up? So this is selection, and then we will have when, at which instant am I going to apply my selection. And here we have 2 classes of algorithms, the non-preemptive ones and the preemptive ones. So the preemptive means that I am allowed to kick out any process from inside the CPU to give the CPU to another process, even if that process is not done executing yet. Fair enough? So this is preemption. The reasons could be different. So P1 could be executing and P2 has a higher priority than P1, so it will kick it out. So it's a preemptive system because P1 is not done yet and it's been chased away from the CPU. Or it could be time slicing. My time is up. I'm not done yet executing, but my time is up. So I'm going to make place for P2 so it can execute. And this is preemption as well because I'm not done. And even though, albeit I'm not done, I'm being kicked out from the CPU. Now question, when I'm being kicked out of the CPU, so when I have a preemptive system, where do I go? So my process that is currently running, where does it go? Does it go to the blocked list? Definitely not, because it's not about a resource. Well, if it's not going to the blocked list, well, it go back to the ready list because it still needs the CPU. However, for some reason, it's not being given the CPU for now. Okay. Easiest of them all, first scheduling algorithm, first in, first out. So from now on, when you see an ascending arrow here, this means that it's the arrival. What does it mean, arrival? Arrival of the process where? So it's the arrival of the process for the very first time in the ready list, in the ready state. Fair enough? So what will go on? Let's try and figure out how the system works. Is it a preemptive, non-preemptive scheduling algorithm? Right, so strict queuing, and among the processes that spend the longest time in the ready state, it will be picked out. You know, the first one that was ready, it will be picked up and sent to the CPU. So let's see, P1 got ready here, you know, it arrived here for the first time, P2 it arrived here, and P3. So naturally, when the time comes and the what do we call it? The dispatcher is going to make a decision. Well, systematically it will go ahead and pick up P1. Now P1 will start executing. What would happen when P2 is ready now? Should I kick out P1? Nope. In, first out, I'll go on until I'm done. And then I'm gonna go ahead and check which one was ready first for the first time between P2 P3, because both of them are in the ready list now. So should I pick up P3 or P2? Well, P2 was here before P3, so I should pick up P2 all the way until it's done, and then I have P3. And you can see here, this is what we call the execution time. It is the time that I need to spend inside the CPU. Fair enough? Preemptive or non-preemptive? Well, no one left and went back to the ready state, so it's a non-preemptive system. Right, so now time slicing, well, we're gonna call it technically from now on round robin. Why round robin? Because it goes round and round and round. Right, now we're gonna ask ourselves a couple of questions, and this is the exact typical analysis that I would ask you in your exam, so I can give you some scheduling algorithm that you may have or not necessarily seen in class before, and I'm gonna ask you a bunch of questions about it. Is it preemptive, etc., and I'm gonna ask you to schedule a bunch of processes using that particular algorithm. So imagine that I'm giving you a round robin for the first time and we haven't talked about it. So round robin time slicing, each process will have a time slice, and it will go round and round between the processes that are in the ready list. So I need to find out if it's preemptive or not, is it fair or unfair, and naturally most of the people in the face-to-face lecture, they answered that it sure looks fair. We're gonna find out later it's not necessarily fair, but for the time being, yes, it might look fair, so we're gonna stick to that for now. So let's see, arrival. 3 processes got ready one after the other, and naturally, because P1 was here first, no other processes was in the ready no other process was in the ready list, so basically P1 will go first, and then we're gonna have some kind of pattern that we're gonna repeat all over again. So check this out. P1 will go for a little bit of time, and then when the time is up, well, I'm going to go ahead and check between the two here. For some reason I went for P2. I could have gone with P3, but for some reason I said that because this one was here first, so I'm going to give it the first time slice first. I'm going to stick to that all the way to the very end. So P1, P2, P3 followed by P1, P2, P3 all the way until I'm done with that. Alright, so the time slice is also known as quantum from now on, right? And the question is how big the quantum should be. So let's try and analyze it together. If I have a really small quantum, this means that every process will progress in a parallel way, in a fast way. However, this is interesting if we have a big number of processes. However, if we have a small number of processes, maybe we can create a big chunk here, and this will help some of the processes to finish early. Because if P1's execution time is just 3 units or something like that, so if I make the quantum 3 units large, fair enough, all I need is 1 slice and I'm done. Then I can share the time between P2 and P3 because P1 will be done. Well, if I have it only 1 unit of time here, only 1 take, well, I have to have 3 time slices for P1 to be over, to be done executing. This is where I stopped with the face-to-face lecture, and this is where I'm stopping right now. The last thing that I'm gonna ask you, well, is round robin preemptive or not? Well, to answer that question again, am I being kicked out before being done? Do I still need the CPU when I was kicked out? You can see that yes, P1 is kicked out here to give space to P2, and it still needed the processor. So it is preemptive. Alright, have a nice one and good luck for your exams.